Welcome to this comprehensive mathematics lecture on areas related to circles, designed specifically for Class 10 students. Circular geometries are not just theoretical shapes. They represent some of the most fundamental structures in both nature and modern human engineering. From the circular ripples that expand outward when a stone is dropped in water to the sophisticated gear mechanics driving industrial motors, circles represent efficiency, symmetry, and infinite rotation. Historically, ancient mathematicians in Greece, Egypt, and India struggled to measure the curved spaces enclosed by circular boundaries. Today, these exact formulas are used in architectural design, mechanical engineering, urban planning, and computer graphics. When structural engineers plan the dome of a circular stadium or landscape designers create concentric garden walkways, they rely on circular mensuration speed calculations to optimize materials and resources. Today, we will master circular sectors, derive arc lengths, solve segment areas with central angles of 60, 90, and 120 degrees, and analyze combination designs step by step. Before we dive deep into advanced circular portions, let us firmly ground ourselves in the foundational parameters of a circle. A circle is mathematically defined as the locus of all points in a plane that are at a constant distance, which we call the radius, from a fixed central point called the center. The total outer boundary length is the circumference. Historically, the ratio of the circumference of any circle to its diameter was discovered to be an invariant mathematical constant, which we designate as the Greek letter pi, approximately equal to 22/7, or 3.14159. Thus, the circumference is represented as 2 times pi times r. The total enclosed surface space, or the area of the circle, is represented as pi times r squared, which can be visualized by dividing the circle into infinite pi-like wedges and reassembling them into a rectangular shape. Mastering these two core formulas is our key starting point, as every sector and segment we calculate today represents a precise fraction of this complete circular boundary and area. Now let us introduce the concept of a sector. A sector is the circular region enclosed by two radii and their corresponding bounding circular arc. A standard visual analogy is a single triangular slice of a round pizza. The area of a sector depends directly on the central angle theta subtended at the center. Because a complete circle represents a full rotation of 360 degrees, a sector with central angle theta represents a precise fraction of the entire circle, which is theta over 360. Since the entire circle has an area of pi times r squared, we derive the area of a sector by multiplying this fraction by the complete area. Thus, the area of a sector is theta over 360 multiplied by pi times r squared. For example, if we have a central angle of 60 degrees, the sector is exactly 60 over 360, which simplifies to 1/6 of the entire circle area. This beautiful, direct linear relationship makes calculating sector areas incredibly intuitive. Just as the sector area is a precise fraction of the complete circle area, the corresponding outer curved arc is a precise fraction of the complete outer boundary, or circumference. The length of an arc of a sector with a central angle theta is derived using the exact same proportionality principle. Because a complete circle boundary represents 360 degrees and has a total perimeter of 2 times pi times r, the arc length subtended by an angle theta represents theta over 360 of that total circumference. Therefore, the formula for the arc length is theta over 360 multiplied by 2 times pi times r. For a sector with a radius of 14 centimeters and a central angle of 60 degrees, we calculate the arc length by taking 1/6 of the complete circumference. This gives us 1/6 times 88, resulting in 14.67 centimeters. Understanding arc length is essential in practical applications, such as calculating the distance traveled by a swinging pendulum or the length of curved highway lanes. Let us now progress to a slightly more complex circular division, the segment. A segment is the circular region bounded by a straight chord line and the corresponding circular arc. Unlike a sector, the segment does not extend all the way to the circle center. Instead, it represents the outer wedge. We classify it into two parts: the minor segment, which represents the smaller area, and the major segment, representing the remaining larger area. To calculate the area of the minor segment, we utilize a brilliant geometric subtraction technique. If we connect the chord endpoints A and B to the center O, we form a central sector OAB and a central triangle OAB. The area of the minor segment is precisely equal to the area of the sector OAB minus the area of the central triangle OAB. The challenge in segment problems is always calculating the area of this central triangle, which depends heavily on the central angle. Today, we will learn how to master this subtraction for 60, 90, and 120 degrees central angles. Let us calculate a practical segment area where the chord subtends a right angle, or 90 degrees, at the center of a circle with a radius of 14 centimeters. First, the sector area is 90 over 360, which represents exactly 1/4 of the complete circle. 1/4 of 616 gives us a sector area of exactly 154 square centimeters. Second, we calculate the area of the central triangle OAB. Because the central angle is 90 degrees, the triangle is a right-angled isosceles triangle, where the base and height are both equal to the circle's radius of 14 centimeters. The area of this right triangle is simply half of base times height, which is half of 14 times 14, giving us exactly 98 square centimeters. Finally, subtracting the triangle area from the sector area, we have 154 minus 98, resulting in a minor segment area of exactly 56 square centimeters. This shows how clean right-angle segment calculations are. Now let us analyze a segment where the chord subtends a central angle of 60 degrees inside the same 14-centimeter circle. The sector area is 60 over 360, which represents exactly 1/6 of the complete circle. 1/6 of 616 gives us a sector area of approximately 102.67 square centimeters. Next, let us evaluate the central triangle OAB. Since the central angle is 60 degrees and the two radii sides are equal, the base angles must also be equal to 60 degrees, meaning triangle OAB is an equilateral triangle. The area of an equilateral triangle is derived as the square root of 3 over 4 multiplied by the side length squared. Using the value of square root of 3 as approximately 1.732, the area of our equilateral triangle is 0.43 3 times 196, which is 84.87 square centimeters. Subtracting this from our sector area, we get 102.67 minus 84.87, yielding a minor segment area of 17.8 square centimeters. Let us now tackle the most advanced segment case in our syllabus, where the chord subtends a central angle of 120 degrees inside a 14-centimeter circle. The sector area is 120 over 360, representing exactly 1/3 of the complete circle area. 1/3 of 616 gives us a sector area of 205.33 square centimeters. To calculate the central triangle OAB, we draw a perpendicular line OM from the center O to the chord AB. This perpendicular altitude bisects the chord and splits the 120-degree angle into two congruent 30-60-90 right triangles. Using trigonometric ratios, the altitude OM is our times cosine of 60 degrees, which equals 7 centimeters, and the half-chord AM is our times sine of 60, which is 12.12 centimeters, making the complete chord base 24.25 centimeters. The triangle area is half of base times height, which gives 84.87 square centimeters. Subtracting this from the sector area, we find a minor segment area of 120.46 square centimeters. Having mastered sectors and segments of individual circles, we now elevate our geometric skill to analyze combination plane figures. In real-world engineering and design, we rarely encounter isolated circles. Instead, we see combinations of triangles, squares, rectangles, and circular segments fitted together to form complex structural components, architectural layouts, or ornamental designs. Calculating the area of these composite figures is like solving a beautiful jigsaw puzzle. The fundamental rule is to identify the simple individual shapes that make up the complete figure. We then use additive or subtractive methods to isolate the desired shaded region. For example, to find the shaded border between concentric circular rings, we subtract the inner circle area from the outer circle area. Similarly, to find the area of circular arches, we combine rectangle areas with circular segment areas. Developing a clear, systematic visual decomposition plan is the secret to solving any complex combination problem. Let us solve a highly famous combination problem that frequently appears in board examinations. Consider a square ABCD of side 14 centimeters. At each of the four corners of the square, a circular quadrant of radius 3.5 centimeters is cut out, representing four corner quadrants. Additionally, a complete circular hole of diameter 7 centimeters, which means a radius of 3.5 centimeters, is cut out from the very center of the square. Our task is to calculate the remaining shaded area of the square. First, the complete area of the square is side squared, which is 14 times 14, giving 196 square centimeters. Second, we combine the four corner quadrants. Since four quadrants of equal radius make up one complete circle, the total area removed from the corners is pi times r squared, which is 38.5 square centimeters. Third, the area of the center circle is also pi times r squared, which is 38.5 square centimeters. Subtracting both cutouts from the square, we have 196 minus 77, resulting in a remaining shaded area of exactly 119 square centimeters. As we conclude this lecture, let us summarize the essential mathematical formulas we have mastered today. First, for a complete circle of radius r, the circumference is 2 times pi times r, and the area is pi times r squared. Second, a sector of central angle theta has an area of theta over 360 times pi times r squared, and its outer curved arc has a length of theta over 360 times 2 times pi times r. Third, the area of a circular segment is calculated by subtracting the central triangle area from the central sector area. For 60 degrees central angle, the triangle is equilateral with area square root of 3 over 4 times r squared. For 90 degrees, it is right-angled with area half of r squared. For 120 degrees, we split it into two right triangles, finding an area of r squared times sine of 60 times cosine of 60. Memorizing these direct algebraic relationships is your ultimate passport to geometrical success. Thank you for studying with us today. Master educational math content like this takes careful geometric design and structural visual planning. If this step-by-step whiteboard lecture helped you understand circular sectors, segments, and combination shape calculations, please take a moment to support our free school learning series. Like this video, subscribe to our channel, share it with your classmates, and leave a comment below about what unit topic you would like us to compile next. By joining our growing digital classroom community, you help us make high-fidelity, high-quality, and robust science and mathematics educational tutorials freely accessible to school students worldwide. Keep practicing your formulas, keep drawing your coordinate lines, and we will see you in our next Class 10 Geometry lecture.